So let me just start by thanking the organizers of this conference, this workshop. I've attended many conferences and many workshops throughout my academic career, and some have made me feel more welcome than others. But this is the first workshop I've ever attended where I have literally felt at home. So I want to thank the organizers for that. I'm sure that they had to do some earth-shattering changes to be able to accommodate us in that way. But I thank them for all the effort that they put into this. My name is Carlos Perez-Delgado. I'm a lecturer at the University of Kent in the School of Computing. And before I get started, very important, I have to mention that this is joint work with Hector Perez-Gonzalez, who is at the University of San Luis Potosí in Mexico, and our work is available at that archive link. Obviously, it'll also show up in the, what's it called? The conference or workshop proceedings. I should say a couple of things. First of all, I'm a quantum computer theorist through and through. I've worked in quantum computing, quantum information for 15 years. Mostly my work has been surrounding quantum algorithms, quantum computation. So I've worked on quantum data structures, for example, a data structure for undirected graphs that allows for quantum advantage in certain operations. Quantum models of computation like super parallel systems like quantum cellular automata, quantum cryptography, quantum cloud computing, secure quantum computation. And the reason I mention all of these is so that you note the one thing I didn't mention, and that's software engineering. I am not a software engineer, even though unlike many of my colleagues in quantum computation, I'm a computer scientist rather than a physicist. I've never really done research in software engineer up until late last year. I was in Mexico for a conference, completely unrelated conference, something on quantum computation. And Hector, my colleague whose photo you see in the slide, he's the head of school at the computer science department at the Universidad de San Luis Potosí. He very graciously invited me to give a talk there. And while I was there, he pointed me to the call for submissions for QSC. And that's when we started talking to each other because, well, he's an expert in software engineering. And I'd like to consider myself as knowledgeable in the area of quantum information. So we figured maybe neither of us by ourselves would be able to contribute to this area, but together perhaps we would be able to say something intelligent or intelligent sounding about the area at least. And that's one thing I'd like to bring up. I mean, the moral of this story is twofold. First is another thank you to the organizers. I think the organizers of this workshop were correct in that now is the time to pull together the expertise from all areas, and they've been successful. Hector and I would not have sat down and started talking about this had it not been for the call for submissions for QAC. So again, thank you to the organizers. And the other moral of this story is that a multidisciplinary field like ours, like quantum software engineering, this nascent field, I think benefits a lot from interdisciplinary collaborations. Interdisciplinary in the sense that, I mean, we're both computer science scientists, Hector and I, but we come from very, very different fields. Working together, we can, I think, accomplish things that neither of us would have been able to even get a stab in by ourselves. Okay, moving on. So this is the outline, formal outline of my talk. So I'll start off with an introduction, and then you'll notice that I've crossed out the first part, why quantum software modeling. The reason for that is that I don't think we really need to go over that with this crowd. I think everybody who is present at this workshop is already well motivated for the topic. And I also noticed that, well, there's 30 minutes per talks, one after the other. What really means should be 20 minutes for a talk, give 5 minutes for questions, 5 minutes for the transitions between talks. And I do have the last talk of the session, so I'm sure everybody wants to go home, such as it is. So I don't want to keep you longer than absolutely necessary. So I'll jump right into the work that we did, which is trying to answer the question, what does quantum software architecture, what does quantum software engineering or quantum programming in the large look like? And I like to stay on this point for a little bit, because even though I'm not a software engineer myself, I do know enough of the area to know that software engineering means a lot of things to a lot of different people. Everything from software testing, from module testing, from formal methods to things like UML, software architecture, software modeling, programming in the small, programming in the large. There's a huge community. So we can't really tackle all of it. I did spend some of my early life as an academic, as a mathematician, and my professors used to say there that it's better to be generalized than to generalize. And so this is our attempt, in short, of trying to think of what quantum software engineering looks like as a whole by focusing on one area, which will be quantum modeling software, and then trying to, put that out there with the idea that hopefully others will come and generalize what we've done here. And we will start that, or I'll start my talk by mentioning what we believe are the essential design axioms for any quantum software modeling language. What are the axioms and what are the principles? These should be taken as general ideas that can be applied to quantum software engineering in any context. Here in this talk and in our paper, we've applied them as an example to UML. And again, it bears noting or spending a little bit of time here explaining why UML. The reason is greed, I guess. Hector and I would very much like for our ideas to go viral. And in that sense, it makes sense to use as a ubiquitous language as possible. And UML is something that is taught to undergraduates in any computer science program around the world, or most, I would guess. I know I learned UML as an undergraduate, and my students learn UML as undergraduates, my undergraduate students. I believe Hector's as well, and so on and so forth. Expertise, Hector is an expert in UML, even though I cannot say I am one myself. But mostly it's the predominance of that language. So what we're going to try to do is introduce minimal principles to extend an already existing language in order so that it can express quantum software. So let me get started with the design axioms. And really, I had two axioms and then I changed one to an observation, and I'll explain why. So I'm really only left with the one axiom, so sorry for the false advertising. So the main axiom of our work is that quantum software engineering, or in this case, as we're focusing on software modeling, should be as similar to classical software engineering as possible, but no more. And here I made a little note, because I know Luis talked a little bit about this earlier. I should start by saying that as an axiom of our work, you're allowed, of course, to agree or disagree with this statement. And if you disagree, there's really nothing I can do. I mean, other than accept that this talk might not be that interesting to you. But I would like to dwell on the axiom a little bit longer and try to convince you that you probably already agree with this, even if you think you don't. Luis was speaking about how with quantum software engineering, we have the potential to start anew and make it all formal. And I don't disagree with what he's saying, but I don't think he and I are disagreeing either. I don't think he would disagree with my axiom. I think that he would suggest that that same formality should also be applied to classical software engineering. So that's my whole point here. I think that in as much as quantum software and classical software are similar, the engineering should be similar. And so how similar is the next question. Exactly how similar is quantum software to classical software? And here's an observation. It was, as I said, I had originally wrote it down as an axiom, but it's not really an axiom. It's an empirical observation. And unlike my previous slide, where you're allowed to agree or disagree, I don't think there's really room for disagreement on this one, because it's just a fact of nature. And the fact is the following, so I'll just read it out. The only difference between classical computation and quantum computation is that the former operates strictly on classical information, while the latter can operate on quantum information. Now, I think on the face of it, this statement can be read as you know, one of those Homer Simpson statements. Well, duh, of course. But there's a couple of subtleties there that I won't point to right away. But I think most of you are already noting the kind of subtle language that I use there, and I'll come back to that. But just in case one of you or some of you disagree with even the generality of the statement, let me point out the following to say, what I'm trying to say is maybe you disagree that quantum software and classical software are that similar to begin with. You think there's a deeper difference. But let's look at this. So this is a textbook, a classic textbook on classical computation or classical algorithms. And inside this textbook, there are things like this, right? Classical algorithms. So this is a circuit diagram. You might prefer to represent your classical algorithms as a pseudocode or as in your favorite programming language. It doesn't matter. Inside a classical computation textbook, there's classical algorithms. And now this is a textbook on quantum computation. And inside that textbook are exactly the same things. Nothing has changed. There's classical algorithms, there's quantum algorithms, and both happen to be algorithms, transformation of information. Nothing at the conceptual level has changed except what these algorithms work on. Now, don't get me wrong here. This is not to say that conceptual distinction is very deep. And of course, it allows for very different computational power and for very different difficulty in terms of trying to come up with new algorithms in those regimes. But from a conceptual level, the only difference is the information upon which these operators, algorithms, act upon. Right. So I think if I'm going to get any pushback during my talk, I would expect it to be here. But I'll move on and assume that everybody is just nodding and smiling. So the question then is, if quantum computation is just like quantum computation, except for what it operates on, can't quantum software engineering modeling languages like UML can't quantum software engineering modeling language be exactly like classical ones? And we just leave the distinction to be understood. And this is an important distinction. And I need to spend a little bit of time here because we're talking about software architecture, right? We're talking about things like UML. So programming in the large rather than programming in the small. And in programming in the large, things like algorithms, things like the specific algorithms that you use are implementation details that you don't really look in. I know that this is important in some areas of software engineering and definitely in areas like quantum algorithms where I tend to spend most of my professional time. But in the context of software architecture, the particulars of algorithms used, you wouldn't say, if you need to sort n numbers, you wouldn't specify that you're sorting them using bubble sort or quick sort, right? You just assume that you're using the most efficient algorithm. So if the algorithms themselves, if what the data they operate on is an implementation detail that is not important at the level of discourse that we care about, shouldn't we just treat quantum algorithms and classical algorithms exactly the same? And the answer to that is a little bit subtle. It comes back to my observation earlier, which is no, because quantum computers can operate on both classical and quantum information. And these are not interchangeable, right? These are different things, right? And again, I can imagine some pushback, some questions. Okay, Carlos, but aren't implementations or hardware details outside the purview of software modeling? Wouldn't a certain module handle classical quantum information data be outside the purview of software engineering, or in this case, software modeling? Certainly UML, again, doesn't care about your hardware, right? So why would we care about this? And there's a few answers to that. And I really enjoyed Marco's talk in particular because he gave one of the answers that I care about. So one, the quickest answer, the most immediate answer is that there's an engineering constraints. Quantum operations and quantum data storage are much more expensive than classical. So if you're designing, even at a high level, quantum software, you want to know which of your modules, which parts of your software can be refactored completely and be implemented completely classically, and which ones cannot. Right. So that's the first answer why we care about the difference between quantum information and classical information, even at this high level software architecture panorama. But there's an even better answer. And before I get to the better answer, let me explain why this answer is not already that strong, because you could potentially come back at me and saying, well, yes, Carlos, this is all nice, fine, and well today because quantum computers are more expensive than classical computers today. But that's just an accident of our location in space-time. It's possible that 20 years from now, 30 years from now, quantum computers will be just as cheap to manufacture as classical computers. So this engineering reason will go away. And you're potentially correct. We don't know that will be the case, but it could be. But we have better reasons. And my favorite reason is the one from physics. Classical data and quantum data, classical information and quantum information are different, not just from an implementation perspective, but they are intrinsically different. You can't store quantum information in a classical device. And there are operations that you can perform to classical information that you cannot perform to quantum information, like cloning. You can clone classical information, except for specific cases, you cannot clone quantum information. So it's not that one is a strict subset of the other. Classical and quantum information are distinct from a fundamental level. The computer science response to why we need to differentiate these is that the input and the output of a module, the data types, are part of that module's interface, right? Even if the implementation details of how that module works are not, what it does to that data, what it outputs and what it inputs is part of that module's interface, and therefore it's a purview of a modeling language or a software architecture. And because those data types can be classical or quantum, again, they become an important part of the discussion. So here we go. In summary, we want to talk about software modeling of quantum software in as close a possible way to the ways we talk about software modeling of classical software. The only difference between quantum software and classical software is the data which they can operate on. Classical software can only operate on classical information, whereas quantum software can operate on both classical and quantum. And we want to know when it is operating on either. Knowing these things, or accepting these things, we can list a set of design principles that any high-level software modeling language, like UML or something more formal, should have to use. And these are it. There's 7 of them, and this is what we've named them: quantum classes, elements, variables, operations, supremacy, aggregation, and communication. Okay, so I will go by them one by one. So the first design principle is whenever a software module makes use of quantum information, either as part of its internal state implementation or as part of its interface, this must be clearly established in a design document. So again, we're talking about a high-level programming in the large software architecture document. You're designing software at this high level. Even at that level, you need to know whether your module makes use of quantum information or it does not. Okay, that's the first design principle. The next one: each module or interface element, e.g. public functions, methods, public variables, and internal state variables can be either classical or quantum. Again, it's a simple statement, and these must be labeled accordingly. Again, even in these high-level design documents. Next one is quantum variables. Each variable should be labeled as classical or quantum. If the model represents data types, so here we can discuss different software modeling languages. If the software modeling language that you're currently using represents data types, then the variables should also specify whether that data type is classical, like an integer or string, or quantum, e.g. qubit array, quantum graph state, data type, etc. Okay, so not all high-level software modeling languages will explicitly include the data types. If they do, then these need to be labeled correctly. And one could argue that if your modeling language of choice doesn't, then it might not be a good candidate for representing quantum software. The next one, and I'm sure you've already, all of you here have heard the term quantum supremacy. We just stole it, borrowed it, because it's appropriate here. So the statement of this principle goes, a module that has at least one quantum element is to be considered a quantum software module. Otherwise, it is a classical module. Quantum and classical modules need to be clearly labeled as such. So the point here is that quantumness is contagious. If your module internally uses quantum information, or it aggregates, well, I'll get back to that in a minute, I guess. If it makes use of quantum information anyway, then it itself becomes quantum. That's I guess the overarching principle of this this principle here, and the next one that I'm going to be talking about, quantum aggregation. So if your module is composed of other modules, and those other modules can be classical or quantum, but if at least one of those modules that it aggregates is a quantum module, then your module is also quantum. Again, the quantumness is viral in our universe of discourse. Finally, quantum communication. Each module's interface element, e.g. public functions, methods, public variables, etc., and internal state variables can be either classical or quantum. And again, these have to be labeled accordingly. So these are the design principles. In summary, you want to distinguish when a module is using quantum software and classical software. I gave you 3 reasons for that. There's the engineering reason that Marco very clearly stated in his own talk, of why engineering costs are just completely different and will be completely different for the foreseeable future of quantum software versus classical software. So if you can refactor your software architecturally so that your classical modules are separate from your quantum modules, and you can run those classical modules on classical systems, then that's a big plus. But I've also given you 2 very important fundamental reasons from physics, from the nature of reality, which is to say that quantum information, classical information are fundamentally different. And they're more fundamentally different than, say, a data type. They're more fundamental to each other than, say, an integer and a float. So there's no real ability here to speak of automatic typecasting or anything along those lines, right? As quantum software architectures, we have to be respectful of the difference between quantum information and classical information. And these are the design principles that can be applied, in our opinion, to any general purpose software engineering initiative, whether it is to extend an existing software modeling language or to create your own from scratch. Now, we didn't want to create our own from scratch. As I said before, what we wanted was to exemplify these principles in real world cases by extending a very well-known existent modeling language, UML. So we've extended UML. We call it QUML. Let's just call it QUML. And these are in one slide, or rather the two-slide version of QUML. So the notation, UML being a very graphical language to represent software graphically, it makes sense that our extensions would also be graphical. So the way we do this is that we represent quantumness in one of two ways: bold and double lines. So if you're using text, we will bold that text. So a module that is quantum will have a bold name, a bolded font. And if there's relationships are between modules, those in UML are more often than not designated using lines. We will double those lines. Very simple. In order to afford ourselves some level of backwards compatibility with existing UML, omitted data types will be assumed to be classical. In UML, you don't necessarily have to specify your data types. You can, but don't have to. So in extending UML, the rule we've said is if your data type is quantum, then you have to label it as such. If it's classical, you don't have to label it. Either way, it's just assumed. Any unlabeled data type will be assumed to be classical. Now the rules. Again, this is the one slide summary of our QUML rules that are, you can just see them as directly taken from our principles and just applied to UML. So a quantum class method can send both classical and quantum messages, but a classical class method can only send and receive classical messages. A subclass of a quantum class is always a quantum class, though the converse does not hold. And aggregation promotes quantumness, association does not. Right, so again, that's the one slide, 30-second version of our QML rules. And next, I just want to show you a couple of examples. So here's a class diagram in QUML for one of the most famous quantum algorithms, the Shor's algorithm. So you can see here, and I was about to point to my screen and then realized that's not going to work at all. But you can see that your top left, you have your Shor application, and that consists of a Shor factoring module. And that's a quantum relationship there. And your Shor factor application consists of two modules. One is a classical module, which is just a Euclidean algorithm. And the second one is Shor order, which is the quantum order finding algorithm. And here we're already, what I like about this slide again is where it's as if I traveled back in time. I came here, listened to Marco's talk, and went back in time and made this slide, because this is implementing exactly what he was talking about, trying to factor out and make it explicit how you can factor out classical modules from quantum modules. So here's an example of what he was talking about as desirable. Here we can see it in practice. Here's one way in which you can do it. Now, Shor order consists of another quantum module, which is a QFT, the quantum Fourier transform on integers. And the quantum Fourier transform is a subclass of a abstract quantum class. That's why it's bold, italics, and bold, which is the QFT. So if you know about quantum information, then you're aware that the quantum Fourier transform is a very general quantum algorithm that can be applied over several different fields, groups. It's a subgroup order finding algorithm. And the particular one of the particular utilities of that algorithm is in finding the order in an integer field, which is what is used then to factor. So this is what Shor's algorithm looks like as a QUML class diagram. And here is the, oh gosh, what is this? The other diagram, sequence diagram. This is a sequence diagram where we see the interactions between the modules. We have our user initiates at the top left the communication. And the interesting thing, so I'm looking at the clock and I'm realizing that I'm running out of time, even though I've already cut down things. So let me just refocus your attention to the bottom right part of your screen, where you see the communication between Shor order and QFTN. And the interesting thing there is that you see that the communication between those two modules isn't always quantum. And so those two modules send each other quantum information when they require. So the first message is setting the input. Short order is telling QFTN that it is to apply QFT to the input cat0. And then it sends a classical message, please give me the QFT of that input that I sent in the previous message. And then it receives the quantum message, the output, which is again, itself quantum. Again, in this diagram, you can see that it is possible to have that level of accuracy where even between modules, you're clearly stating which interactions are classical, which interactions are quantum. And it's in a very readable and concise fashion. So in summary, as this field advances, I think the most important principle, or we took it as an axiom here, is that software engineering for quantum software is not in itself a brand new field, but rather has to be built upon the existing fields of software engineering, of course, quantum information. Quantum software engineering doesn't have to be altogether all that different from classical software engineering. We just have to be respectful of the fact that quantum information and classical information are different. And that's my talk. So, questions?
Thank you, Carlos, for the great talk. Any questions? Shoka, please.
Yes, thanks a lot for a very great talk. And I was just wondering, since we work a lot in modeling, so how do you, since in UML, for example, you will also have these state machines, and then when we go to describing, for example, state invariance for the states to precisely describe states, and then we have classical states, and then we will have quantum states. And how do you see that? How can we precisely describe quantum states, for example, to model the dynamic behavior of a quantum program?
That is an interesting question, and I don't have a full answer to that at this point.
Yeah, so no, I was thinking, for example, if we think about, see, there is this Dirac notation to specify, but that will be very difficult for software engineers, right? So if, for example, if I want to extend OCL, for example, to specify state, I'm not sure, I have no answer. I have no answer too, I'm just trying to.
So let me just throw out some ideas there. I earlier said that the only difference between quantum algorithms and classical algorithms is that the information that they operate on. But even then, the difference is not as drastic as some might think. It's really drastic if you're going from classical deterministic algorithms to quantum algorithms. There, the difference is drastic. But on this road from classical to deterministic to quantum is something that classical computer scientists have been dealing with forever, which is probabilistic algorithms. And the jump from probabilistic algorithms, which the field of modeling probabilistic algorithms is vast and complicated. So I'll definitely not go into that. But when going from modeling probabilistic classical to quantum, all you're doing, quote unquote, is changing a probability density function with a quantum density function. These things are not that different. You're changing your Markov operators with unitary operators. Again, those things are not that different. I think Luis will probably have better things to say about the intricacies of looking at states and saying something formal about them. In my work with Hector, we really focused on the high level view of software engineering. But I did want to say that because I don't think that it's as big a hill to climb as some people might think. A lot of the tools have already been developed, or similar tools have been developed in the context of probabilistic computation.
Okay, can I have another follow-up question? So
yes,
you see, So you see that you told that all the classical information can be represented as a quantum information, right? For example, it's
Sure. I mean,
so
you can take classical information and represent it in a quantum device. Absolutely. That's
so
axiomatic. Yes.
so if we think from that perspective, and then why do I need to separate, for example, tagging quantum variables different than the other variables?
For the three reasons that I gave. So let me just spend a little bit of time. Marco actually gave a very good explanation from an engineering perspective. Storing quantum information is a lot more expensive than classical currently, and it will continue to be so for a long time. So if I have a variable that is a classical variable, and I can store it in a classical physical device, then noting that in my design documentation can save me a lot of money later on when I implement it.
No, I understand. I understand. Maybe I didn't put my question.
Yeah, maybe I didn't
So,
understand your question.
so what I was trying to say that, for example, in UML, at UML level, not the low level.
Yeah.
So if I have defined a new data type like a quantum integer,
Yep.
and then I have normal integer. So because when I do modeling, I would like to have minimum changes to things, right? I don't want to introduce extra stereotypes. I don't want to have extra tags because why if I can avoid them? So if I have a class diagram, I have two variables. One is, let's say, quantum integer something, and one is normal integer. So if I have this kind of thing, I don't need to maybe tag,
Yes. No, I see what you mean. And for that, where is... For that, let me point you at the third point here, physics. Classical data and quantum data admit different operators, right? So you can't copy quantum data.
Sure.
There's a no cloning there. So even at that level of design that you were talking about, if there's a variable and I don't know whether that variable is quantum or classical, then I don't know what type of operations I can operate at a fundamental level. Like classical software engineers never have to worry about whether they can copy a data type, right? This is just assumed that you can, because you always can. But in this case, you might be able to, or you can't. And if you don't know whether a data type in particular is quantum or classical, then you don't know whether you can clone it. You don't know it. You don't know whether it can, like observing it can collapse it. These are important distinctions that are fundamental, and they're fundamental at the information level. They're not implementation details, is what I'm trying to say. And unlike Marco's answer, it doesn't have to do with the cost or the engineering. It has to do with how your software operates. If your software has a variable that cannot be cloned, there are certain things that have to happen. Even the type of operation. I mean, I'm hyper focusing on cloning because I think it's the easiest example. But all quantum computation has to be reversible. That puts constraints on the type of operators that you can.
No, I fully agree. No, I fully agree with you. I think my question is more about the design of, but it's okay. We can discuss later because I fully agree with you what you said.
I guess Shanta trying to say that because UML is the abstraction because we do modeling. If you do the tag, say that this is the quantum class, another is not. This kind of tagging might help to do the transformation, which you do from the UML to implementation to quantum software program, which is necessary to have these tags, I guess, in the models. Yeah.
But yeah. So what I mean, I was thinking maybe about the variables, that instead of having tagging each variable, which could be quite require a lot of effort to tag, I could maybe create a library of quantum types and I can just use them. So in this way, I don't need to tag them, but when I do transformation, I know which variables are quantum and which are not. So I was thinking in that direction.
No, that's okay. I think I understand your point now, and yeah, I think that's a fair point. I don't think you need necessarily to tag,
Yeah.
to specify the particular data type. You just really need to specify whether it's quantum or classical.
Yes. Yeah.
So there is a bit of that already in our design of QUML, which is to say that we specify that if the output of a method is quantum, then we boldface the name of the method. And that's just to tell us that what it's outputting to us is going to be a quantum message, and maybe we don't have to specify the data type. Just bolding it is enough. Yeah, that's a very valid point. Sorry, I had not completely understood what you were saying until just now.
Yeah. Okay. I think we have time to take the last question. Tom, you can. Yeah.
Okay. Thank you. So I have a question. Might the no cloning theorem imply further rules to the modeling in QUML? Because obviously, I mean, then I can't pass quantum variables to more than one other class, for example. So I just assume we need more rules for the no cloning theorem.
So there is a lot of things that you can and cannot do depending on whether your software, your data is quantum or classical. And I guess on first admission, I would say that we did not list them all in our paper. It would have been a little bit longer than the 3-page limit. But yes, one of them would be, you can't just take the same as cat psi, your quantum variable, unknown variable, and send. You can't multiplex.
Mm-hmm.
That's it. You can't multiplex. There's a few other constraints, which I think this comes back to what Marco was saying, is that you want eventually to be able to have a design language that somebody who doesn't understand any quantum mechanics can use. I don't think we're there yet. I'm not sure that we can be there. I feel that understanding quantum information, at least at that level, is necessary to be able to operate in this field. If I'm going to be manipulating these symbols, I mean, I think the purpose of the language, like QUML, is to make it easy for me to understand what the properties are of the objects that I'm manipulating. So whether an object is quantum or is classical, that's important to me. What I need as a researcher, as a designer, as a software architect, to know what those differences imply. So I don't think the modeling language itself is the onus is on the modeling language to tell you, well, you can't multiplex quantum information. No, I think the onus on QUML is to tell you, oh, hey, look, this is quantum information. You know what that means. And then the software architect has to know, yeah, okay, that means I can't multiplex. Thanks. Moving on.
Okay, yeah, I agree. Thank you very much for your answer.
Okay, so we have a last question. Luis has been raising hand for a long time. Luis, go ahead.
Yeah, thank you. Just to, yeah, that's a very interesting talk. I'm just a comment to say that I clearly agree with you that we should do quantum software engineering as close as possible to the classical case. I would have that, but no closer than that. Yeah, I think. And one issue that I think it's completely relevant and somehow relates to this discussion we're having now has to do with typing. I think we do need strong type systems for quantum computation. The annotation of data as classical or quantum is just a starting of this, but if you're able to encode the real properties of our programs and our data through a suitable type system, this will certainly increase quite a lot our expressive power, and mainly than that, our reasoning power about quantum software. Yeah, thank you very much for your talk, Henry.
No, thank you. And for your talk and for your comment. No, sorry, I should be more careful. I probably shouldn't have called you out I didn't mean to call you out. I use your name because what you said
That's
earlier.
Perfect, no problem at all.
I agree with what you were saying, and I wanted to make it clear that I wasn't disagreeing with you.
Okay, thank you.